good afternoon to all of you, and thank you for being here. So I'm Luigi Borzi from the Department of Control and Computing Engineering, and today I would like to talk about wearable technology and artificial intelligence techniques for monitoring movement disorders. So first of all, movement disorders are a class of neurological conditions that includes, for example, multiple system atrophy, tremor, and Parkinson disease. They are different from each other, but they share an impaired movement control, such as involuntary movements, slowness, postural instability, and a reduced coordination. Among movement disorders, Parkinson disease represents the second most common neurodegenerative disorder. It affects more or less a quarter of a million subjects in Italy, and we have more or less 20,000 cases in this region. So basically, the disease is due to the death of some dopaminergic neurons in a certain region of the midbrain, and a lack of dopamine leads to uncoordinated movements, an impaired movement control, attention deficit, and alterations in mood, cognition, and sleep. So several motor and non-motor aspects are related to the disease. Today I will focus on the motor ones. For example, bradykinesia is described as the slowness in performing movements, or postural instability is related to the risk of fall, but also walking impairment, including freezing of gait, which is a sudden motor block, and I will show you a video, and I would like to talk also about this today. So, what is the problem with Parkinson disease? First of all, some non-motor aspects of the disease manifest up to 20 years before the clinical diagnosis, but they are not detected, neither by the patient and by neurologists. The diagnosis is mainly based on some motor symptoms, such as the slowness of movement, rigidity, and tremor, which probably is the most well-known symptom of Parkinson disease. And then we have other motor aspects, which appears in the late stage of the disease, and they are very difficult to appreciate in a medical office. So we have to provide a monitoring in the home settings, and it has to be continuous. So in order to provide an objective evaluation of movement, we have different solutions. So first of all, we may use optoelectronic systems, which basically consist on a set of markers which are attached on your body, on your limbs, and then a set of cameras which record the position of each marker, but they are very costly. So we may choose to use RGB camera and extract the exoskeleton from the human body and then analyze the position of each limb. Or if we want a portable system, we may use wearable sensors that can be worn on the subject's body and can record the human movement continuously, and also outdoor and also in the home setting. And finally, we have to consider that motion sensors, inertial sensors, are embedded in smartphone, for example. So we don't need additional hardware. We may exploit the widespread technologies such as smartphone for recording data and analyze signals. So I have to say, inertial sensors are small, lightweight, wearable, low power, low cost, and they can be worn on the subject's body. And nowadays, we have a lot of both prototype and commercial solutions that vary in cost, weight, size, and so on. And we have to consider also that smartphones and smartwatches embed inertial sensors. At the same time, while recording data in this ecological manner, we need some complex and sophisticated computer methods for analyzing movement data. And we may choose to use statistical analysis, signal processing, machine learning, and more complex deep learning. And the combination of artificial intelligence techniques and wearable technology may help providing useful information about mobility during the day, the response to treatment provided by a neurologist, but also to get information about the progression of the disease and the risk of fall. So this is the overview of my PhD project. It starts with the acquisition of data from a large population of healthy and subjects with Parkinson's disease. And the data is recorded using smartphones or commercial or prototype inertial measurement units. And then I have to say simple activities are analyzed, such as walking, turning, standing, and so on. So activities of daily living. And data are analyzed using signal processing and machine learning to provide an objective evaluation of the patient and to detect some motor symptoms and to estimate their severity. So the first symptom I would like to talk about is bradykinesia, which is the slowness while performing movements. It is important because it is one of the earliest motor signs of the disease. So the clinical diagnosis is mainly based on bradykinesia, and the symptom worsens over time and is responsive to treatment. So the automatic detection of bradykinesia is important for the early diagnosis of the disease, the evaluation of the progression, and also to get information about the response to the therapy. So in this case, 93 patients with Parkinson's disease were recruited. A single smartphone was used for recording data. The smartphone was attached to the subject's thigh, and subjects were asked to sit in a comfortable position on a chair and to rise and stamp each foot at least 10 times, as fast as they can and as high as they can. And then this is an example of the data we have to analyze. So on the top left, you can see this is angular velocity. So this is velocity, not acceleration. And on the top left, you can see a normal movement. You can see that it is very regular and the amplitude does not decrease. And on the bottom right, you can see a very impaired movement. So from these, we can decide to extract some information. It is called features related to the amplitude of the movement, to the frequency, and to the regularity. And then from these features, we can sort them in order of importance and select just some of them, the most important one. So in order to train supervised classification models, you have to provide features as input and also what is the objective, what is the target. So in this case, 4 different clinicians provided the score for each task. So we have 4 different scores. They were combined using the mean. So we have as target the average clinical score. And then different models were trained using this data and the performance were evaluated. So as you can see here, the artificial neural network provided the best performance. And as you can see from the plot, the error was less than 1 point in a scale from 0 to 4 in all cases, and it was less than a half point in 80% of the cases. So it was really precise. But also, I would like to show you these. These are pie charts from the 4 different neurologists. As you can see, the scores provided are very different from each other among clinicians. And if we compute the correlation between the model and the average clinical score, this is either than the best agreement between clinicians. So we can state that smartphone can be useful to evaluate bradykinesia in Parkinson's disease. We have to consider inter-rater variability, and in this particular case, which is a very simple task, so a very simple movement, the system performs better than each single clinical rater. So this is one of the advantages of computer methods. But this is a very specific task, so it is not true in general. For more complex tasks, such as walking or turning on complex activities, it is not said that computer method can be better than human eyes, let's say. So I would like to carry on with freezing of gait. So I would like to show you a brief video. This is a patient with Parkinson's disease. He is walking, and then while he is turning, this is freezing of gait. Patients experience, they feel like their feet are glued to the ground and they are not able to walk anymore. This symptom can last from seconds to minutes, and it is related to a high risk of fall. In addition, it is very difficult to evaluate this symptom in a medical office. So, in this case, data from 3 different datasets were used for a total number of more than 100 patients. A single sensor was used for recording inertial data, and it was placed on the lower back, so on the waist. Basically, what is done is take acceleration signals, segment them, so divided into pieces. Each piece is input to the classification model, which in turn provide the output, and then we can evaluate the performances. So clinicians label the signals, and then the model outputs some prediction, and you can evaluate the performance between the model and the ground truth, we can say. So this is the model. If you are not confident with this is a convolutional neural network. Basically, we can say that it consists in 2 parts. The first part, it is the feature extractor 1. So it extracts automatically features, the most important features from the signal, and then it passes to a kind of artificial neural network, which consists of neurons. And they provide the output, which is a probability of a single window of being freezing of gait or not. So this is about performance evaluation. So on the top you can see the label by clinicians. So they say that in that moment there was freezing of gait, just that. And then the prediction of the model overlaps for a certain part, and also we can see that the part that overlaps, this is a true episode. So it is true that freezing of gait episode manifested, and in these other cases this is a false positive because you know, the system said that it was freezing of gait, but it was not, as you can see from the blue line. And also we can compute the time between the occurrence, the start of the episode, and the time in which the system identified the episode. It can be predicted before the actual occurrence or detected with a certain delay. So these are the performances. We can say that the system works properly. Most of the episodes are detected, so you can see 100% cases in one dataset and 87% in the another dataset. And maybe the most important point is that the system was able to predict the episode, the freezing of gait episode, before the actual occurrence. Let's say, on average 3 seconds before. And then the other half of the episodes were detected in 1 second. so in 0.8 seconds, which is quite good because this allows for the early detection of the episode, and this can be important for providing some kind of auditory, tactile cue, which can reduce the duration of the episodes, but also prevent the occurrence. So, and also it is very fast. So it just needs 40 milliseconds for classify each window. So the algorithm is now implemented in a, let's say, wearable solution. It consists in a sensor on the back which records inertial data and two vibrating anklets which can provide vibration on the ankles. And this, from literature, is known to reduce the duration or even prevent the episodes. And this is very important to reduce the risk of falls. So the system works in the following way. The sensor on the back records data. In real time, it at present transmits data to a personal computer. The computer embed the deep learning algorithms, and so the data are processed, and if a freezing of gate is detected, then the anklets are activated. So once we will experiment this system, the wearable solution will be standalone, so we don't need anymore the PC, and it will run all on the wearable sensors. So, summarizing, we can say that we can monitor Parkinson's disease using wearable technology, but we have to decide the number, the type of sensors, and also the position on the body. And also, we know that computer methods can provide very accurate measures, but at the same time, they need to be robust. And also, we have to choose between classic machine learning and more sophisticated deep learning, which in turn is less interpretable. And finally, I have to say that Parkinson's disease is a very heterogeneous disorder. So an adequate, let's say, a very large number of patients is required for making the algorithms working properly. So I would like to thank you for the attention, and I will be very happy to answer to your questions. Thank you very much.